lesson 5 from chapter 10. This is another early morning screencast, so you may hear a little coughing in the background on occasion. Sorry for that. We're going to wrap up our thoughts on the properties of alcohols. Remember, alcohols have that hydroxyl group, one or more of them, somewhere around the outside, the periphery of the chain of carbons. And our simplest one, of course, is going to have just one carbon. And so this would be our simplest alcohol. And one carbon means meth. So instead of talking about methane, we knock off a hydrogen, stick a hydroxyl group in there as our substituent. And now we have methyl alcohol, often called methanol with the OL ending. It's a very small molecule. That means its intermolecular forces can be relatively weak. That means it's going to be a gas by the time it gets to room temperature. And let's see, what else can we say about it? Oh, it's I'm sorry, I was thinking about methane. Methanol is a liquid and doesn't become a gas until 65 degrees Celsius. And that's because of this hydroxyl group. That hydroxyl group gives it some polarity. Remember, it's going to have two lone pairs, so you're going to have a negative side, which means you go from those induced dipole forces to polar intermolecular forces. Because of this polarity, that makes it dissolvable in water, because water is polar and methanol is polar. Now they can dissolve in any proportion, any relationship. So you can have 10% methanol, 90% water, or 90% methanol and 10% water, and anywhere in between. These two liquids are completely miscible. They can dissolve in any proportion at all. The same would be true with ethanol, the two-carbon alcohol, which is the alcohol that is in alcoholic beverages. And sometimes in alcoholic beverages, it gives you the proof, and the proof is always twice the percentage of alcohol in the beverage. Now, people should not be drinking any alcoholic beverages at all until their brain is pretty much fully formed in their early to mid-20s. Sadly, that is not always the case. The first time I ever had any alcoholic beverage was in a communion service after college. The communion wine was indeed wine. Of course, that's such a very, very small quantity, and wine has a relatively small percentage. Beers are usually about 4 or 5%. Wines might be, say, 10 to 13%. And then these generally involve a fermentation process, but eventually you get to a distillation process where you can make the alcohol concentration extremely high. Once again, a rule of thumb about alcoholic beverages is the Bible doesn't say the alcoholic beverage in and of itself is wrong, but it does say being drunk is wrong. And the reason for that is when someone is under the influence of alcohol, they are not able to discern right from wrong as readily. There are many other issues as well, but that's one that is often overlooked. God wants us always to be alert, because the devil goes around like a roaring lion, seeking whom he may devour, to quote scripture. So we want to always remember that when the Bible says thou shalt not, that you should not be drunk, isn't just referring to alcohol, it's referring to anything that can be so addictive you cannot discern right from wrong. That's a principle of scripture. Well, let's move on. One thing you can do when you think about alcohols is to imagine the water molecule And if we knock off a hydrogen and put a methyl group there in its place, now we have methyl alcohol. And then if we were to put another, make that a 2 and put another methyl group attached to it, now we have ethanol, a 2-carbon chain. So you can think of alcohol as being derivatives of water, just like later in this screencast we'll think about amines as being derivatives of ammonia. Of course, you can also knock off this hydrogen and put a methyl group in that place. And now you have an ether with methyl groups or ethyl groups or carbon groups on either side of your oxygen. So both the ethers and the alcohols can be considered derivatives of the water molecule. You're used to thinking about carbon as being the starting point, and then you add an attachment. You can also think of water as your starting point, and then your methyl group is what you substitute in. Now, as far as whether or not alcohols are soluble in water, whether or not they have high or low boiling points, all depends upon their intermolecular forces, your IMFs, which we cover in chapter 12. The more polar the molecule, the stronger the intermolecular force. And a superpolar molecule would be when your intermolecular force is because you have the presence of a nitrogen or an oxygen or a fluorine. And then it becomes a hydrogen bond. And of course, alcohols have this oxygen in there. So the hydrogen bonds are extra strong dipoles or polar molecules and create therefore extra strong bonds between the molecules, which results in requiring more energy to separate the molecules when you go from a liquid to the gas state. And we're also reminded of the fact that the smaller molecules have a more extreme dipole, a stronger polarity, and they're going to be more soluble. Remember, like dissolves like. Molecules which are alike will dissolve in each other, and two molecules that are not alike, like polar and nonpolar, will not dissolve in each other. Here's another example of a relatively small molecule that can dissolve in water. You have one hydroxyl and two dry hydroxyls off of your two carbons. So it's 1,2-eth for two carbons, ethano, di for two hydroxyls. 1,2-ethanoldiol, which nobody really calls it that. The industrial name is ethylene glycol, and when you go to the store to purchase some, or you go to the auto mechanic to get your car ready for the wintertime, they check the antifreeze level. Antifreeze, of course, is going to depress the freezing point and raise the boiling point. It's a colligative property that we'll be talking about later in the book, because the presence of the ethylene glycol molecules in the water elevates the boiling point for water, so that the engine has to get a lot hotter before the water in the coolant system boils, and it depresses the freezing point. The temperature has to get a lot colder before the water will freeze. So the smaller ethylene glycol molecules sort of interfere with both the crystallization process of freezing and the boiling process as well. Now, you might recall back in page 459 in the previous screencast, we saw a table, and we looked at the fact that as the molecule gets bigger and bigger and bigger because you're attaching more and more carbons to it, its molar mass, of course, then gets bigger and bigger and bigger. And the bigger it gets, two things are going to happen. One thing that happens is you're going to have a lot more electrons all over the place. And remember what an induced dipole is. An induced dipole, if this is the molecule, and you got all these electrons all over the place, when this thing moves around and gets close to other molecules or collides with the sides of the container or with each other, these electrons can become, the cloud of electrons can become distorted, and you end up having more electrons on one side than on the other side, inducing a negative pole and a comparative positive pole. That's your induced dipole. And so the bigger the molecule, the greater the molar mass, and the greater the molar mass, the more likely you're going to have times when you have an induced dipole. And that, therefore, creates stronger intermolecular forces, which will, of course, change the freezing points and the boiling points. But the other thing that's going on is as your molecule gets longer and longer, the nonpolar side sort of loses touch, so to speak, with the polar side. So if you look at this molecule right here, it's a very small molecule. You have a very distinct negative part of this molecule, where those pairs of electrons around the oxygen, the lone pairs, are. So you have a electrostatic potential surface that is very, very negative. By comparison, very, very positive. So you have a pretty strong dipole. And we can do it like this. You sometimes see the arrow where the positive sign is the back of the arrow with a crosshatch, and the tip of the arrow points to the negative region of the molecule. Sometimes you see little marks like this with the negative and the positive, Greek symbol representing the negative regions and the positive regions. Now, when we come over to this molecule and we add 3 more carbons, excuse me, you'll notice that the degree of my dipole here is not quite as much. I'm going to make it as a smaller arrow. Not as big a region of blue, not as big a region of red. Not only that, but this side of the molecule was getting farther and farther away from the polar side of the molecule, and pretty soon we might get something like this, where we have a really, really non-polar part of the molecule, far away from the polar end of the molecule. And we're beginning to look at the way in which soaps work. The reason why soaps can wash non-polar materials like grass stains and oils and greases and blood off of plates and silverware and cups and clothing and rinse it down the drain is because the non-polar end will dissolve the non-polar contaminants like the grease and the oil, and the polar end will dissolve in the water. And that's how soaps work. And of course, this polar region is much more complicated than just a simple hydroxyl group. Now we move to a whole new category of hydrocarbons. Little sip of coffee there to help. These are amines. And you should be used to this word, or you need to get used to the word, because it means there's nitrogen in the hydrocarbon somewhere in the organic molecule. Later on, we'll talk about having nitrogen and oxygen in the same molecule. But right now, put oxygen aside and focus just on adding nitrogen. And one way to look at amines as being derivatives of ammonia. So if I make an ammonia molecule here with my lone pair of electrons, and I say I'm going to knock off this hydrogen here, and I'm going to put a methyl group in its place. Well, now I have an amine. I have methylamine. And if I have another 2-carbon branch on there, now I have ethylamine. And of course, I can also stick a methyl group in place of that hydrogen and a methyl group in place of that hydrogen and make more and more complicated amines. So this is a way of looking at the ammonia molecule as being the precursor for the amines, like we just looked at the water molecule as being a precursor for alcohols. In organic amines, 1 or more hydrogen atoms are replaced with an organic group, which is what I just showed you right there. And you might remember that because of this lone pair, right there, because of that lone pair, Ammonia can gain a proton by sharing that pair of electrons with your hydrogen nucleus, and then it becomes NH4 plus. And you might remember that makes this a Lewis base because of the coordinate covalent bond, which is what we call when you share 2 electrons instead of 1. And Lewis bases give 2 electrons. This then would become a Lewis acid because it would be receiving electrons. Nitrogen is giving 2 electrons, and the proton is receiving 2 electrons. Those are Lewis acids and bases. So when we talk about protonation, that means adding the H plus to make either hydronium or ammonium. And deprotonation goes the other way. So if I take my NH3 and I take this proton and remove it, now I have NH2 with a minus sign. And so both the water molecule and the ammonia molecule can protonate or deprotonate. Because of nitrogen, we would expect trigonal pyramidal structures. That would be the geometry around the nitrogen atom. We can also have primary, secondary, and tertiary amines. So if you look at this carbon right here, and I'm going to go back to red, look at this carbon right there. It has 1 nitrogen attached to it. Or to turn it around, the nitrogen, the amine, the NH2, the NH2 is going to attach to a chain of carbons, and we could have another carbon, another carbon, another carbon, and so forth. But this carbon right here, when the amine is attached to it, would be called a primary amine because it's attached to a carbon that has 0 or 1 other carbons attached to it. Now, the amine here, this amine with only 1 hydrogen is attached to a carbon there and attached to another carbon over there. This makes it a secondary amine, not a primary amine. And then my amine right here, my nitrogen right there, this is going to attach to 3 carbon chains that can be 1 or more carbons. So this would be a tertiary amine. So on a test, if you want to know whether an amine is primary, secondary, or tertiary, you look to see how many carbons are attached to the nitrogen. This is different than in the alcohols. Remember, in the alcohol, it could look like this or like this. So in this alcohol right down here, it could be methyl, ethyl, we can keep going, propyl, but this carbon is only attached to 1, 0 or 1 other carbons. So this would be a primary alcohol. When we look at this one over here in the middle, you'll notice that this carbon is attached to 2 other carbons, 1 there and 1 there. This makes it a secondary alcohol. And over here, you'll notice that this carbon is attached to 1, 2, 3 carbons. That makes it a tertiary alcohol. So keep in mind that the way we look at primary, secondary, and tertiary amines is different than the way in which we look at primary, secondary, and tertiary alcohols. And you will need to know that. That would there's going to be something like that on the test. What are the properties of amines? Usually they kind of stink. And when I say stink, I mean really stink. We find amines in urine, excuse me. Urine is when the urea molecule begins to break down, and when it breaks down, one of the gases it releases is ammonia, which is why a container of wet diapers, for example, really begins to stink. It's in rotten meat, which I'll mention in a minute, and bad breath. Now, here are two very interesting amines. You see the word amine there and amine there. And you'll notice that this has 1, 2, 3, 4 carbons. This one has 1, 2, 3, 4, 5 carbons. So we have buta for 4, penta for 5. And then you'll notice we have an amine there and an amine there, and on the other molecule on opposite sides. So this molecule, the amines are attached to carbons 1 and 4. Doesn't matter which way you number the carbons. And over here, the amines are attached to 1 and 5, either way that you number. And they are called putrescine, which means it smells, it's putrid, rotting meat, and then cadaverine. Both of these are the kinds of amines that are created as flesh and meat decompose and rot. And cadaver dogs that are searching through ruins after an earthquake, or maybe they're looking for a dead body somewhere. We think, we don't always know what a dog is detecting, but we think they're looking for this odor even from hundreds of yards away, because they're able to smell extremely small concentrations of gases like this that we cannot detect as human beings. The smallest amines, again, are going to be water soluble, because the smaller the amine, just like the smaller the alcohol, the more polar it is, and like dissolves like. Most amines are not, because once you get a couple carbons and an amine on place, it begins to have a higher molar mass. It begins to become a bigger molecule, and the forces of attract, intermolecular forces, get greater, and they become insoluble. Amines generally behave as bases, and that means that when they react with acids, they give salts. And so if we look at some of these molecules down here, we got an amine attached to a ring structure. And so you can see that we have the alternating double and single bonds, or we could have just done the more accurate resonance structure. So we could call this amidobenzene, with the emphasis on the benzene molecule, or whenever we have the benzene ring as an attachment, it's called phenyl with a YL, not to be confused with phenyl with an OL. Phenyl with an OL, by the way, has a hydroxyl group. It's in the alcohol family. Notice the OL. But phenyl with a YL is when this benzene ring is the attachment. So we could call this phenyl amine. Phenyl amine. But it has an industrial name called aniline or aniline. And of course, being a base, it can it can chemically react with acids and make salts and water. And this would be the anilinium ion over here. And that the cation would be whatever the other part of the molecule would be in the salt. Now, there are some very famous amines that you should know. Here's the highly addictive nicotine. A number of years ago, cigarette companies were called out for adding extra nicotine to the cigarettes in order to make them addictive. One of the things about the cigarette industry is eventually your best customers die of lung cancer and heart disease and things like that. So you got to replace them with new customers. You got to capture people, especially younger people, a lot faster and get them addicted. So they were doping their cigarettes with additional nicotine. Very, very highly addictive. It does not necessarily interfere with brain chemistry, but you've got other types of amines. You're thinking of caffeine and cocaine and things like that. I think that'll all be talked about a little bit later. Just to give you an idea of how insidious nicotine can be, we use it as an insecticide. So people who smoke cigarettes are getting not only are getting basically an insecticide into their lungs, and it is, and then of course when it's absorbed into the skin, it becomes in different forms. It can become a very more potent poison. I did a biology experiment one time back when I was teaching biology with my students, and we took some Daphnia shrimp from some pond water, and we added a very, very, very dilute solution of this nicotine. And it did increase their heart rate, but it also shortened their lifespan. So this is a good time for you to pause the screencast and see what you know. Now we're going to talk about the carbonyl. And I've heard this word here pronounced many different ways. I pronounce it carbonyl, carbonyl, and it seems like the emphasis is supposed to be on the first syllable, carbonyl. So if I mispronounce it, it's from years and years of saying it in different ways, depending upon where I heard it last. So the carbonyl group is a double-bonded oxygen. So this would be your simplest, I just said carbonyl. Carbonyl, this would be your simplest carbonyl compound right here. And then, of course, you can make longer and longer chains of carbon. And you can also put, if your chain is long enough, like this one, you can put your double-bonded oxygen, your carbonyl, off a middle carbon instead of off an end carbon. And you need to know for the test and to understand organic chemistry that when you're that over here, when your carbonyl is at the end of your chain, this makes it a member of the aldehyde family. And when it's somewhere in the middle of your sequence of carbons, it makes it a member of the ketone family. You need to know the difference between a ketone and an aldehyde. Now, at this point, we're going to look at this case study, which is kind of interesting. Here you see Robert De Niro and Robin Williams, who is deceased, in their roles, playing an individual who had a form of sleeping sickness, which is especially true in equatorial jungle regions as far as a very debilitating infection. And they one doctor began to treat an individual who for decades was in this sort of zombie state. And don't read more into it than that, than descriptive. Began treating this individual with L-DOPA. L stands for left-handed, where the word L actually comes from the Latin for left, levo. D is for right-handed, dexterous. And it's amazing how many molecules, organic molecules like amino acids, are all left-handed but not right-handed in their mere isomerism. And this particular molecule seemed to play a role in helping this individual live a much more normal life. In your brain, you have all kinds of neurotransmitters. You might recognize serotonin. which is very important in your in melanin. I think that's the right name. I don't want to confuse it with the pigment that's in the skin. But anyway, there's two brain neurotransmitters that are involved in your sleep cycle. That's important not to disrupt. But this particular L-DOPA is very important in terms of your mental health. So one of the neurotransmitters in your brain is called dopamine. And dopamine is very essential in helping you with your movement, in your mood, in your motivation, in your memory. Those are 4 words that comprise your mental health: movement, mood, motivation, and memory. When you're really sluggish and you're in a brain fog and you just have no inclination to do anything, you feel like kind of like a zombie without all the blood and the hunger for putrid flesh. It could be the sign of low dopamine. Well, one of your amino acids, remember your proteins are made of sequences of amino acids, about 20 different amino acids. One of them is tyrosine, and when tyrosine metabolically becomes this molecule right here, L-DOPA, and then L-DOPA helps in the formation of dopamine, this essential neurotransmitter in the brain. These are also very closely related to this particular amine, epinephrine, also known as adrenaline. And with my asthma years ago, before we had the modern medicines, on emergency situations, I'd have to get a shot of epinephrine because I was barely breathing because my air passageways in my lung were so terribly blocked. All right, let's move on here and resume our conversation about carbonyls. The simplest one is called methanal. And the IUPAC names, they end in AL, just like for the IUPAC names for alcohols ended in OL. And the IUPAC name for attachments ended in YL. Alcohols were OL. Aldehydes are AL. But nobody calls this methanal. They call it by a name that's been around for centuries, formaldehyde. It's the simplest aldehyde. And then, of course, you can have ethanal and propanal and butanal as your carbon chain gets longer. Later, we're going to talk about carboxylic acids and the carboxylate ion that has both a carbonyl and a hydroxyl at the same time. And I've already mentioned ketones, which have the carbonyl off of a middle carbon somewhere between the two ends. Doesn't have to be exactly in the middle. So this one here has the everyday name that everybody calls it, acetone, but technically it would be called 2-propanone, because ketones end in O-N-E, 2-propanone. And of course, propanone can only have one isomer, and that's the carbonyl off the middle carbon. So sometimes the 2 is just dropped because it's understood. So you can have propanone and butanone and so forth. But they all have this carbonyl. So your carbonyl is there in the aldehyde. Your carbonyl is there in the ketone, where R represents carbon chains on either side. In the carboxylic acid, remember, I don't like that. I would prefer to do this, where that oxygen, the first one, is my carbonyl. And then as far as esters are concerned, I'd like to keep those R's separate, where one of those oxygens is the carbonyl and the other oxygen would be part of a hydroxyl. And then we have amides, which have both the carbonyl and an amine. And you need to know all of these and recognize them when you see them. And at least in the basic sense, you should be able to name the simpler members of all of these different families of organic compounds. Now, all of them are aldehydes, ketones, and carboxylic acids can be considered oxidation products of alcohols. So when you take a semester or year-long course in organic chemistry and you spend hours in the lab doing organic synthesis, you might begin with an alcohol and then synthesize some other organic compounds from that. For example, well, we'll get to the, let's go ahead and look at this down here. Let's say here I have an alcohol. And this alcohol has one or more carbons. There's the one necessary carbon, and this could be 0 to 1, 2, 3, 4, 5, etc., more carbons. Here's my hydroxyl group right there. Now, when I oxidize this with an oxidizing agent, and an oxidizing agent would be a compound that would have lots of oxygens in it, in the formula, you can see it in the formula. With the right catalyst and temperature, you can create an aldehyde, which means you turn the single bond into a double bond right there. And you can also then oxidize your aldehyde. And now not only do you have the double bond, but now you have another single bond. And now you've created the carboxylate ion, and you have a member of the carboxylic or organic acid family. So you can go from alcohols to aldehydes to carboxylates through the oxidizing process. And I'll leave it to you to confirm that the oxidation number for the carbon to which the hydroxyl or carbonyl is attached goes from a -2 oxidation number to a 0 up to a +2 oxidation number. Now notice this is a primary alcohol. Remember, the primary alcohol means that your hydroxyl group is attached to a carbon, and the carbon to which it's attached is either attached to 0 other carbons, like in methanol, or it's attached to 1 other carbon in the rest of the chain, as opposed to a secondary alcohol. So let's come down here and look at a secondary alcohol. Notice in my secondary alcohol, this carbon is attached to 2 carbons, not just 1. So it's a secondary alcohol. And when you oxidize this, you're going to get a ketone instead of an aldehyde. When you oxidize a primary alcohol with its hydroxyl at the end of your carbon chain, or technically we'd call it the beginning of the carbon chain, you create a carbonyl at the beginning of the carbon chain. When you have a secondary alcohol, your hydroxyl is attached to some carbon in the middle of your chain, therefore your carbonyl will be attached to some oxygen in the middle of the chain. And we take advantage, by the way, of this oxidation process in the breathalyzer test, when, for example, a police officer might test to see whether or not a driver is driving under the influence of alcohol, because it produces a chemical change. Some potassium dichromate will be present as an oxidizing agent, if I remember correctly, which has all those oxygens in it. And as that compound is being used in the oxidizing process, the color changes from the yellow-orange of the dichromate to the green of just the chromium. And you could calculate the oxidation number for chromium in the dichromate ion. And then you can see that the oxidation number for chromium is +3. So the changing oxidation number of this transition metal produces a color change. Here are some common oxidizing agents that you should recognize: potassium permanganate with all of its oxygens, and here's your potassium dichromate with all of its oxygens. Here's a tertiary alcohol, and they have a tendency not to be oxidized. Now, The difference again between aldehydes and ketones is the presence of that carbonyl group being off the end or off the middle. Now, this is one of my favorite parts of aldehydes. You have those horrible smelling aldehydes, but you also have and amines, but you also have those wonderful ones. My three favorite smells and flavorings are the flavorings that come from almond paste in pastries, and you find the same flavoring in cherries. So cherry pie I love, and then I love cinnamon, and I also love vanillin or vanilla. And all three of these molecules have very, very similar molecular structures. So here's the aldehyde that makes the almond cherry smell and flavoring, and here's the one that makes the cinnamon smell and flavoring. And you notice both of them begin with our benzene ring and have an amine attached to it. Benzene, it's amazing that benzene itself, by itself, is carcinogenic, cancer-causing. But as soon as you put attachment on it, you change you change all of its properties, and now it becomes something wonderful in the baking and flavoring industry. That's something that the people that fight the drug war often encounter. We encounter a brand new synthesized opiate, for example, and for which there is no law against. That's starting to kill people and addict people, and so the law enforcement informs the politicians. The politicians pass a law to ban this new derivative, and so the chemists that work for the drug industry, the illegal drug industry, say, okay, we'll just change the molecule a little bit. Stick a methyl here, knock a methyl off over there, and it has similar properties, and now they put that on the market, and more people die and get killed or become addicted. You can also have reduction reactions, and reduction reaction requires reducing agents. Notice the reducing agents have the hydrogens in them as opposed to the oxygens in them. So just like we can turn an alcohol into an aldehyde through oxidation, the other direction we turn the aldehyde back into an alcohol. And you see that my oxidation number is getting smaller. And we can do that with the primary and the secondary alcohols as well. Here are some more examples with my 1 carbon, 2 carbon, 3 carbon. And then, of course, we can have our names when we begin to have branches. So you can have a methyl group attached to a 3 carbon chain. So there's my, let's see, I'm sorry, this is my 2 carbon chain and my 1 carbon chain. This could be called a methyl ethyl ketone. That's technically, it's not this systemic or the IUPAC name. Butanone, because it's 4 carbons in a row. No attachments, excuse me. But we could put attachments on there and begin to add them. For example, you could have a 3-methyl butanone by sticking a branch right there. Notice that your boiling point gets bigger and bigger as the molecules get bigger and bigger and have more, not necessarily more polarity, though there is a polarity because of the double bonded lone pairs of oxygens, but the induced dipoles become bigger as well. Carboxylic acids. With the carboxylic acids, the most common is acetic acid, and we make all kinds of compounds beginning with acetic acid. 1 billion kilograms of acetic acid annually, and we turn it into plastics and synthetic fibers and fungicides and all kinds of things. There's citric acid in fruits, which I have to avoid because when I was working on my PhD, I worked every Saturday, I worked every holiday, I worked during the summers. And I remember when I started the program, they said, this will affect your health. And I naively said, nah, it's not going to affect mine. part of my rationalization for that was I'm a Christian, I can handle stress, and that was naive of me to think that that means I can burn the candle at both ends and not be affected. Well, I did overdo it, and I ended up getting that acid reflux that affected my vocal cords, and for a couple of years, I had to teach with a microphone back in the old building. That's from that citric acid. My wife and I were just looking at the label on the grape juice this morning at breakfast, and and she checks to make sure there's no citric acid in there. Formic acid, which is the simplest carboxylic acid with the carbonyl and the hydroxyl and the hydrogen. We would call this methanoic because oic is the name of the carboxylic acid family members. Meth means one carbon, but everyone calls it formic acid. It's found in ants. And we can also take that acid and make formica, which is the laminate for tabletops. Butyric acid is found in rancid butter, which really stinks. So you should be able to name those. Now you find these hydroxyls and carbonyls oftentimes in carbohydrates of various kinds. And I'm conscious of how long my screencast is going, and I think I'm going to have to stop here because we've already gone about 45 minutes. So we'll pick up with this a little bit later.